Welcome to our exciting chapter on motion in a straight line. From the cars moving fast on the road to the planets orbiting the sun in our solar system, everything around us exhibits motion. Even objects in space, like comets and shooting stars, follow a specific path as they move across the sky. In this chapter, we will explore the fascinating world of kinematics, the study of motion in a straight line without considering the forces behind it. In this video we will discuss the following topics. Rest and motion. What is scalar quantity and vector quantity? Concept of distance and displacement and concept of speed and velocity. Let us start with rest and motion. Rest and motion are fundamental concepts in the study of physics. An object is said to be at rest if it maintains a constant position with respect to its surroundings, while an object is said to be in motion if it changes its position over time concerning a reference point. For example, consider a person sitting in a chair in a room. The person is at rest with respect to the room as their position does not change over time. However, if the person stands up and starts walking, they are now in motion concerning the room, as their position changes over time. In a straight line motion, the object moves in one direction without changing its path. For example, a car traveling on a straight highway. We can determine whether an object is at rest or in motion by examining its velocity, but to do so, we first need to understand the concepts of displacement and velocity. Before learning about these concepts, let's first understand the basic concepts of scalar and vector quantities in simpler terms. Scalar quantities are physical quantities that have only magnitude, that is, a numerical value but no direction. They are described by a single number. Examples of scalar quantities include mass, speed, temperature, and distance. Mathematically, scalar quantities can be represented by real numbers, such as 5 kilograms mass, 7 meters per second speed, 30 degrees Celsius temperature, and 20 meters distance. Vector quantities, on the other hand, have both magnitude and direction. They are described by a numerical value along with the direction in which the value acts. Examples of vector quantities include displacement, velocity, acceleration, and force. Mathematically, vector quantities can be represented by ordered pairs or triples of real numbers, depending on the dimensions. That means ordered pairs for two-dimensional or 2D space and triples of real numbers for three-dimensional or 3D space. For example, let's consider a Cartesian plane a two-dimensional space. In this context, scalar quantities can be represented by a single number like 5 units distance. Vector quantities can be represented by an ordered pair, such as 3, 4. To visualize this in the Cartesian plane, you can draw a point at the coordinates 3, 4, representing the endpoint of the vector. The vector itself is an arrow starting from the origin 0, 0 and ending at the point 3, 4. The point indicates movement 3 units to the right, horizontal direction, and 4 units upwards, vertical direction. Using Pythagoras' theorem, the magnitude of this vector is the distance from the origin to the point 3, 4, which is under root of 3 squared plus 4 squared is equal to 5 units. The length of the arrow represents the magnitude, 5 units, and the arrow's direction is from the origin to the point 3, 4. Now, since we have understood scalar and vector quantities, let us discuss the concept of distance and displacement. Let's discuss them side by side, with examples and their mathematical representation. So, distance is the total length traveled by an object without considering the direction. It is a scalar quantity, which means it only has magnitude and no direction. While displacement, which is the shortest distance, takes into account both the distance and the direction of the movement. It is a vector quantity, which means it has both magnitude and direction. Now, mathematically, distance can be represented as the absolute value or the total length of path traveled from initial point to final point. For example, if you walk 5 meters to the east and then 3 meters to the west, the total distance traveled is 5 plus 3, which is equal to 8 meters. On the other hand, mathematically, displacement can be represented as the difference between the initial position and the final position of an object. Using the same example, if you walk 5 meters to the east and then 3 meters to the west, the displacement is 5 minus 3, which is 2 meters to the east. Note that displacement can be positive, negative, or zero, depending on the direction of movement. Now let us take an example to understand the distance and displacement with the help of a Cartesian plane. Imagine a person standing at the origin point 0, 0 on a Cartesian plane. The person decides to walk 3 units to the right along the x-axis, reaching the point 3, 0. Then, the person walks 4 units up along the y-axis, reaching the point 3, 4. In this case, the total distance the person walked is 3 units to the right plus 4 units up is equal to 7 units. However, the displacement is the shortest path from the starting point to the ending point. In this example, it is the straight diagonal line from 0, 0 to 3, 4. Using the Pythagoras theorem, the displacement can be calculated as the square root of 3 squared plus 4 squared is equal to 5 units. So, the displacement is 5 units in the direction of the point 3, 4. Having gained an understanding of distance and displacement, let's now discuss some key takeaways related to these concepts. First, the displacement can become zero, but distance can never be zero if the object is in motion. For example, imagine you are walking from point A to point B in a straight line, and then back to point A. The total distance you traveled would be the sum of the lengths from A to B, and then from B to A. However, since you ended up back at your starting point, your overall displacement would be zero, as there is no difference between your initial and final positions. Secondly, displacement can be equal to distance, but in any scenario, the displacement can never exceed the distance, because the displacement is the shortest possible distance between the initial and final points. Now, by keeping the concept of distance and displacement in mind, we will move to speed and velocity. Speed and velocity are two terms often used interchangeably in everyday language, but they have distinct meanings in physics. Let's look at them side by side using examples related to motion in a straight line. Speed is a scalar quantity, which means it only has a magnitude and no direction. It measures how fast an object is moving. The unit of speed is typically meters per second. While velocity is a vector quantity, which means it has both magnitude and direction. It measures the rate of change of an object's position. The unit of velocity is also meters per second. Now, how do we calculate speed and velocity? Speed is calculated as the distance traveled divided by the time taken to travel that distance. Example: imagine a car traveling in a straight line on a highway at a constant speed of 60 km per hour. This tells us how fast the car is moving but doesn't provide any information about the direction in which the car is moving. While velocity is calculated as the displacement, change in position, divided by the time taken to travel that displacement. Example: now, let's consider the same car traveling at a constant speed of 60 km per hour, but this time, we will also mention the direction east. This means the car has a velocity of 60 km per hour to the east. By specifying the direction, we are now describing the car's velocity, not just its speed. Let us now understand speed better by discussing uniform and non-uniform speed. Uniform speed is when an object covers equal distances in equal intervals of time. In simple terms, it means the object is moving at a constant speed without changing. For example, if a car is moving at a steady speed of 60 miles per hour, it will cover 60 miles in 1 hour, 120 miles in 2 hours, and so on. Non-uniform speed is when an object does not cover equal distances in equal intervals of time. In other words, the object's speed is changing. For example, when a car accelerates from a stop sign, it starts at 0 miles per hour and increases its speed until it reaches a specific speed, like 40 miles per hour. The car is not covering equal distances in equal time intervals because its speed is changing. In conclusion, understanding the concepts of rest, motion, scalar and vector quantities, distance, displacement, speed, and velocity is essential in the study of motion in a straight line. These basic principles lay the foundation for deeper exploration in kinematics and physics as a whole. Remember that scalar quantities have only magnitude, while vector quantities have both magnitude and direction, and this distinction is crucial in differentiating between distance and displacement, as well as speed and velocity. We hope that you have understood these topics of motion in a straight line. Now, here is a secret on how you can study effectively with the Theorem app. You can learn with chapter notes, watch video lectures, and solve NCERT-based MCQ tests of this chapter on Theorem. And that's not all, you also get amazing courses for Class 11 and 12 physics and much more for your NEET preparation. Thank you.